Okay, the material that we need from the previous lecture is written here. We had the definition of alpha square by this equation, then remember lambda was defined to be equal to that, and of course the rho, the new variable which is related to r by this relationship. And then we found that to get acceptable solutions we have to impose the condition that lambda is equal to a number n. We also found that n should have the minimum value 1, then the next possible value is 2, 3, 4, etc. And we were in the process of eliminating lambda and alpha, so that you will have an expression for E. So, let me do that. Lambda is equal to n. So, I am going to put here n, and I shall get an expression for alpha. So, what will be alpha then? It is going to be mu E square divided by h cross square n 4 pi epsilon 0. This will be your alpha. So, alpha square I can easily calculate, it is going to be mu E square divided by 4 pi epsilon 0 the whole square 1 divided by n square h cross to the power of 4, and that should be equal to minus 2 mu E divided by h cross square, because alpha square must be equal to minus 2 mu E by h cross square. So, you can rearrange this, what will be the expression for E? You will find that E is actually negative, because I take the negative sign to the other side. Then you find that it is equal to mu E to the power of 4 divided by 4 pi epsilon 0 square n square h cross square. Is that correct? That is not completely correct. I have a 2 missing, I suspect. So, I have a 2 here. Correct me if I am wrong, but I think I am correct this time at least. So, you find that allowed energy levels are dependent upon this number n that we had introduced. Only if allowed energy levels are given by this expression are you able to get an acceptable solution, otherwise you are not going to get an acceptable solution to the Schrodinger equation. And you also notice that E is dependent upon this quantum number n. So, I want to make this explicit by putting a subscript n. And not only that, when lambda is equal to n, you look at this equation which I have shown on the board. When lambda is equal to n, you can replace this lambda with n, and it so happens that this equation again is very well known to the mathematicians. They were already studied earlier, and therefore, again for these things we do not have to actually make use of recursion relations to find the functions, but we can use the knowledge from mathematics and just try to use those functions. Okay. So, they turn out to be functions which are which were discussed by Liguori, and we will come to the functions. Okay. And now, let me recollect what we were doing. We had the Schrodinger equation for the hydrogen atom. Remember, this is the equation appropriate only for internal motion. We also had an equation describing the translational motion which we got rid of, that I am not writing. So, this is just internal motion. We have the equation H I is equal to E psi. What is it that we have done? We have assumed that psi may be written as a product, if you remember, capital R, capital theta and capital phi. And we solve the equation for capital phi. We will see the solution in a few seconds. I mean, we will see the solution once more, but if you remember, the quantum number m arose in connection with that solution. By imposing the condition that the wave function is acceptable, we got the quantum number m, the so called magnetic quantum number. Then we looked at the equation for capital theta, we found that capital theta, the equation actually contained m. If you remember, I can show it to you once more. Okay, this is here is the equation for capital theta, and you notice that it contains m, right. So, the solution is going to depend upon m, and further we have acceptable solutions only if this constant beta is equal to L into L plus 1. This is something that we have seen. So, the solution actually depends upon the quantum number L as well as the quantum number m. In fact, it depends only upon the magnitude. We will see that magnitude of m, not on the actual value, but only on the magnitude of m. So, therefore, we will explicitly say that theta depends upon L and m. It is a function of small theta, and then today we found the solution for capital R. Capital R has an equation which, for example, is shown here, right, and you find that the equation contains L, it also contains the energy, but energy is dependent upon the principal quantum number n. So, therefore, you realize that capital R actually will depend upon the values of n and L, right, and so this is the general nature of the solution. This is how the solution appears, and so my wave function psi, it depends upon all the 3 quantum numbers. Again, I would also like to stress that there are only three quantum numbers that have come out of the solution, only 3, n, L and m. Okay. And the allowed energy levels are given by this expression. The expression is written here, and it is the expression, exactly the same expression that was obtained by Bohr according to his theory. But now you see, we are not assuming any particular orbit. Bohr assumed that there are certain orbits, only those orbits are allowed, and so electrons were following specific paths around the nucleus. But that is not what we are saying now. We are saying that each electron is characterized by its wave function, and what we have obtained here is the wave function. Okay. And let me now talk about these functions a little bit. Capital phi, we have actually studied them in detail. So, these are the forms of capital phi. Capital phi in general it would have the form 1 by square root of 2 pi e to the power of I m phi. This is the general form of capital phi, and there that quantum number m takes the values 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. Right? Can take all those values. Specifically, if you say that m is equal to 0, then the function is just a constant 1 by square root of 2 pi. If you say m is plus 1 or minus 1, right, if it is plus 1 you have that solution, while it is minus 1 you have that solution. Similarly, you can go on writing the other solutions, it is very straightforward. But you should notice that if m is plus 1 or minus 1, what happens is that the solution is actually containing square root of minus 1. Right, I is there, this is quite fine, there is absolutely no problem with this, but it is rather difficult to visualize a wave function which contains both a real and an imaginary part. It is difficult, okay, because you have to plot the real part, then you have to plot the imaginary part, and then think of its magnitude and so on. So, chemists actually do not make use of these functions, these two functions they do not use. This is something that I have already told you. What they do is they combine these two, or instead of they can combine these two and get solutions which are of this form. For example, you can say get a solution which is of the form cos phi, but then that will have a normalization factor of 1 by square root of pi, or you can get a solution which is of the form sin phi and the normalization factor is again 1 by square root of pi, right. Not only for this case, when m is equal to plus or minus 2, you can do exactly the same thing and you will get solutions which are of the form cos 2 phi or sin 2 phi. Let me make it a little bit clearer. If you had m equal to plus or minus 2, you are going to get e to the power of I 2 phi or e to the power of minus I 2 phi. But e to the power of I 2 phi actually contains a cosine of 2 phi plus I sin 2 phi, right. You know this result from mathematics. E to the power of I 2 phi actually contains both cosine and sine. So, what you do is you actually combine these two so that you will get only the cosine or only the sine. The advantage is that the solutions are then real and you are able to visualize it. Chemists usually prefer to have functions which they can visualize. So, that is regarding the phi functions, and then if you think of the theta functions, okay, I have told you the solutions how they are obtained, and I have also told you that you can get these functions by using recursion relations. And if instead of doing that, we can make use of knowledge available from the mathematicians. Okay. Remember how we went about the process of doing the solution. Actually, we said that we have the function theta and that we changed the variable to z. Z was defined to be cos theta, if you remember. We changed from cos theta, right, small variable theta to something called z. Z is defined to be equal to cos theta. Oh, it has. And then remember we had put 1 minus z square. I mean, like maybe I should write this. Let me just remind you the process of solution. We had the function theta of small theta. We made this change of variable z is equal to cos theta, and the function was then denoted by the symbol p. P was a function of z. And then what we do? We substituted p is equal to 1 minus z square to the power of m by 2 into g of z, and then we found an equation for g. So, if you look at the things that are written, see, you find that 1 minus z square to the power of m by 2 there, and this is actually your g, right. This is your g, but written in a notation that is familiar, that is borrowed from mathematics. So, therefore, what happens is that this is actually your g, and if you wanted to calculate the g, what should you do? It says that you have to take the mth derivative of PL, that is what this equation says. And what is PL? PL is defined by this equation. PL is defined to be, well, there are these derivatives. Maybe I will use these definitions to calculate one of the functions. For example, let me imagine that I am interested in theta 10 of small theta. Okay, suppose I am interested in that. The formula will give me that square root sign. Why do you have this factor square root of 2l plus 1 into L minus m factorial divided by L plus m factorial, and there is a 2 here. You should recognize that this is nothing but a constant which multiplies the function. Why do you have such a constant? The answer is extremely simple. This is the normalization factor. Any wave function would be multiplied by certain things so as to ensure normalization. So, the normalization factors for these functions have been calculated, and it is just that. And in this equation, if you are interested in in this particular function you will have to put L equal to 1 and M equal to 0. That is how you will proceed. So, put L equal to 1 and M equal to 0, we will do that, and then this is multiplied by d to the power of 0 by dz to the power of 0 of P Lz. And specifically if you say L is equal to 0, L is equal to 1, you are going to get 3 by 2. This will be 1 factorial divided by 1 factorial square root d to the power of 0 by dz to the power of 0 is just no operation, you will get P1 of z. That is all. I mean, this is fairly straightforward. And what is P1 of z? That is defined there. P1 of z according to the last line would be given by 1 by 2 to the power of 1 factorial d by dz, right. It says to the power of L, but I have put L equal to 1 into z square, sorry, operating upon z square minus 1. This is your function. And what is this? You can carry out the differentiation. Z square minus 1, if you differentiate, you are going to get 2z, and that 2z and these 2 are going to cancel. So, you will simply get the answer z, right. And so, what is theta 1 0? That may be this value of Pz may be put back here, and so the answer is going to be square root of 3 by 2 into z. I mean, the answer, as you can see, it is fairly simple. Square root of 3 by 2 into z. What is z? Z is nothing but cos theta, because z is our variable that we had introduced, and therefore theta 1 0 of theta is actually simply square root of 3 by 2 cos theta, right. So, in a similar fashion, if you are interested in any particular solution, any particular theta, let us say L is equal to 2 and M is equal to 0, you can just use this formula, right. I do not think I will do other examples, but it is fairly straightforward. All that you need to do is, if L is equal to 2, just put 2 here, and maybe L is equal to 2 and M is equal to 1. That means, you see, you will have to put L equal to 2 here, instead of that 0 you will have to put 1 there, and then you go ahead and do the calculation, you will get the function, right. So, the functions which are calculated in this fashion, I think they are probably there in the next few slides, but before I do that, let me look at the capital R, the function capital R. Capital R depends upon n and L, and it is a function of small r. And it is a little bit, I mean, this is more messier than the previous one. The previous one itself, you may say it is a little bit messy, but if you look at it, it is not that difficult. You can, for any given values of L and M, you can easily calculate the function using the formulae. So, capital R in a similar fashion can be calculated using this formula. You look at this expression, well, there is a constant here that I have not yet introduced, but I will introduce. What is that constant? Well, we have defined rho to be equal to 2 alpha r. What was alpha? Alpha is equal to mu e square divided by h cross square 4 pi epsilon 0. So, let me do that, let me write that. So, rho is equal to 2 times mu e square divided by n h cross square 4 pi epsilon 0 into r. Okay. Agreed. And now this constant, this whole thing, I am going to call it 1 by A0. That whole thing is 1 by A0, so that I would have 2 divided by n A0 into r to be equal to rho. Now, you may ask, why did I do that that step, why did I introduce this A0? The reason is that A0 is something that is very physical. Remember the Bohr theory. In the Bohr theory, you are saying that the electron follows circular orbit, and there is this first Bohr orbit with the quantum number n equal to 1, and that has a specific radius. If you remember, that radius is nothing but this A0, right. If you looked at the expression, you can go back and look at the expression, you will find that this, what is the definition of A0? A0 is defined by this equation, 1 by A0 is equal to mu E square divided by h cross square 4 pi epsilon 0. So, if you define A0 to be this, then it is just the radius of the first Bohr orbit. Okay. So, now if you look at this expression, you have rho equal to 2 divided by n A0 r, and what is capital R? Capital R is defined in terms of rho we have already defined, as well as A0 as well as the principal quantum number n, right, which we have encountered. So, this is the definition, and why do we define, why do you have this part here, this part? Answer is extremely simple, you want the wave function to be normalized. So, this is just the normalization factor. Okay. And then remember, in our method, in our solution solving process, we had actually introduced e to the power of minus rho by 2. Remember, in the solution we had said there is this e to the power of minus rho by 2, and then we had introduced a rho to the power of s, and found that that rho to the power of s is actually rho to the power of L, because s is equal to L. So, therefore, rho to the power of L, then the remaining part is written here. These are actually known as Liguori Polynomials. Okay, Liguori, the name is here, it is a French name, I do not exactly know how to pronounce it. French names are not usually pronounced the way they are written. You do not follow the spelling and pronounce it, but that is what I have done, Liguori Polynomial. So, how do you calculate a Liguori polynomial? The prescription also is given here. You see, you have to follow this definition. It depends upon two numbers, p as well as s. Let us say LP, LS, sorry, LP and S. Where you see here, for example, capital L depends upon n plus L and 2L plus 1. So, you have to imagine that n plus L is written as p, and 2L plus 1 temporarily we can write it as S. Then LPS is actually defined to be a derivative of LP, and what is LP? LP is defined by this equation. Maybe I shall demonstrate this by taking one particular case, right. We do not have the time to discuss all cases, but one particular case, let me take, which case should I take? Maybe not the simplest possible case, let me just say R21, so that it will be a little bit complicated. So, if you think of R21, what is going to happen is I am going to have minus 2 by n is 2, so I 2a0 to the power of 3 n minus L minus 1. So, 2 minus 1 minus 1 factorial divided by 4 into 3 cube, right. I am jumping some steps. I have just substituted the values of n and L in this expression, right. In this expression I have substituted the values of n and L. N is equal to 2 and L is equal to 1, and then what would I have left? I would have e to the power of minus rho by 2, rho to the power of L, where L is 1. So, rho capital L 3, and 2L plus 1 is how much? 3. So, that is my function, right. What does it work out to be? 1 by a0 to the power of 3, this is 0 factorial, which is 1, divided by 4 into this is 27, to the power of half e to the power of minus rho by 2 rho L 3 rho. This is what I have. Okay. Now, what is L 3 rho? Well, I realize I have not taken one of the easiest. I mean, this may be a little bit difficult. Let us see. L 3 rho is actually third derivative of L 3 rho. How did I get that? You just look at this expression. You just look at this expression. P is 3 and S is 3. So, you just use that, you will find this. And what is L 3 rho? L 3 rho is 1 by 2 to the power of 3. I am using the, oh no, that is not correct. It is equal to e to the power of rho d cube by d rho cube rho cube e to the power of minus rho. Okay, I realize that this is a little bit difficult for me to perform. I can do it, but it will take time, right. Okay, I think I will work it out. I can actually work it out using a computer program called Mathematica, but I don't think I will do it now. It's fairly easy if I use the Mathematica program. So, what would be the answer? I think I shall leave it as an exercise. I shall work it out and show you in the next lecture, right. So, this is how the calculation will proceed. So, once you have determined these things, you give me any value of n, L, m. I have given you how to calculate phi. We know how to calculate phi, that actually is very simple. We know how to calculate theta and we know how to calculate r, right. It is only a question of substituting the values and doing these steps that we have seen just now, and so you will get the total wave function. So, let us look at these functions one by one. Now, again I should introduce a few definitions. Actually, this part of the wave function, if you look at it, that determines how the wave function changes as you go away from the nucleus. It is referred to as the radial part of the wave function, right. How does the wave function change as you change the distance of the electron from the nucleus, while the remaining parts, they are dependent only upon the angles. This is dependent only upon the angles theta and phi. And what do these angles determine? If you remember, these angles actually determine different directions in space. They do not say anything about the distance of the electron, but they say in which direction the electron is located, right. So, this is referred to as the angular part of the wave function, while that is referred to as the radial part of the wave function. And further, usually this product is denoted by the symbol y with a subscript L and the subscript m, and it is a function, it is written as a function of these two angle variables, which actually denote directions in space, as I have told you. Again, the reason is that these functions were studied by the mathematicians. These functions are known as spherical harmonics. Okay. These two together are known, are denoted as capital Y and they are known as spherical harmonics. So, let us look at the wave functions one by one. If we looked at the expression for energy, where is my expression for energy? The expression for energy is actually sitting here, right. You find that there is this minus 1 by n square. This is actually of the form, the energy is of the form minus 1 by n square into something which is a constant. That is how the form of the energy is. So, if you put n equal to 1, remember n is a quantum number which can take the values 1, 2, 3, 4, 5, 6, etc. You would realize that n is equal to 1 will be the lowest possible state of the system, because if you put n equal to 1, you are going to get minus 1 into that constant there. If you put n equal to 2, you will find a number which is greater than the previous one, because you see it is the same number multiplied by multiplied by 1 by 4, or the same number multiplied by 1 by 9 when you put n equal to 3, and therefore, the lowest possible state of the system, which we usually refer to as the ground state of the hydrogen atom, will be obtained by putting n equal to 1. So, let us say I am interested in that state, wave function psi n is 1, and we had derived these conditions on the quantum numbers. Whatever the conditions, n has to be an integer greater than or equal to 1. So, we have taken 1, L n minus 1 has to be greater than or equal to L. This is another condition that we have derived, and the third condition was that L has to be greater than or equal to magnitude of m. These were the conditions that we derived, and therefore, if n is 1, second condition implies that L can have the value only 0. That is what you find, and if L is 0, m can have only the value 0. So, therefore, if the moment you say n is 1, L has to be 0 and m has to be 0, there is no other way, and this is the only solution with n equal to 1, and that solution has energy which will be obtained by putting n equal to 1 here. So, that is the ground state of the system, and what do you find? The ground state of the system has only one solution. We say that this is an energy level that is non-degenerate. If you have more than one state, you say it is degenerate, but here there is only one state having this particular energy. So, what is the form of this function? Well, it is going to be R10 of small r, right. What am I using? I am using this expression R10, and the other part is capital Y. I will use the notation capital Y 00 of theta phi. But what is capital Y 00? This means that L is 0 and m is 0, correct. So, it is actually going to be theta 0 0 of small theta into phi 0 of small phi. This is what it is, and this we have already evaluated. Its value is 1 by square root of 2 pi, and this one I hope I have it in my tables, which we will make use of. Okay. Well, it is not given separately, but the, let me see, I thought I, okay, all that happens is that theta 00 is just 1 by root 2. It is not in my tables, but the result is just if you calculate it, you will find that it is 1 by root 2, and therefore, y 0 0 actually happens to be 1 by square root of 4 pi. And R10 itself is written here. Right, I told you how to evaluate this, so I will not go into its evaluation. If you look at this expression, there is a small chance that you will get confused because there is a capital Z sitting there. I will tell you what it is, but there is this A0 which you are familiar, and then to the power of 3 by 2 and 2 into e to the power of minus rho by 2, rho is already defined. So, what is this capital Z? Well, you say this particular expression is valid not only for the hydrogen atom, nuclear charge is unity. It is also valid, if you remember, I said the treatment that I am going to give you is valid even if the nuclear charge is 2 positive charges or 3 positive charges or any number of positive charges, but only 1 electron. And then this equation that is written there is valid for any value of the nuclear charge, where it has been assumed that the nucleus has a charge of plus capital Z into E. So, imagine that the nucleus is actually having Z positive charges, so that the net charge is Z into E, and there is only 1 electron. So, this will be valid for helium ion, it will be valid for Li 2 plus or beryllium 3 plus and so on. For helium He plus, the value of Z will be 2, but because we are interested only in the case of the hydrogen atom, all that I need to do is I will take this expression and say that because I am interested in the hydrogen atom, this Z is simply equal to 1. Okay. So, what will happen? R10, we know how much it is actually equal to this is equal to 1 by A0 to the power of 3 by 2, 2 e to the power of minus rho by 2, and multiplied by y 0 0 that we have found is 1 by square root of 4 pi. And what is rho itself? Rho is defined to be how much? 2 alpha r, that is fine, but I have another expression. Here is this other expression sitting. In terms of A0, rho is equal to 2 divided by n A0. So, in this case n is 1. So, rho is nothing but 2 by A0 into r. So, combining all these things, I will get psi 100 to be equal to 1 by A0 to the power of 3 by 2, 2 e to the power of minus r by A0 into 1 by square root of 4 pi. This is my final answer if I did all these things. Right. And now, this, remember, this is radial part of the wave function, and that is the angular part of the wave function. What has happened? You see, this is very interesting, because the angular part, even though I say that is the angular part, it is just a constant. Correct? It is just a constant. There is no theta or phi occurring in that expression. The radial part, of course, it depends upon the distance of the electron from the nucleus, which is small r. So, what is the conclusion regarding this wave function? See, I want to understand this particular wave function, and here I also would like to introduce a very important word, which I am sure you are very familiar with. This solution that I have obtained represents what? It is the wave function for the electron in the hydrogen atom. Hydrogen atom, of course, has only 1 electron. So, any 1 electron wave function is referred to as an atomic orbital. So, this is an atomic orbital. You give any possible values for n, l and m. the result is an atomic orbital. Okay. And what we have found is the wave function for the ground state. This is the wave function for the ground state. So, this is the atomic orbital for the ground state of the hydrogen atom. It has the quantum numbers n equal to 1, L equal to 0 and m equal to 0. So, it is I 100 and it is actually your atomic orbitals 1s, right. It is the 1s atomic orbital as we are going to see. Now, you look at the angular part is just a constant. This means that if I had the nucleus here and I think of a point somewhere here, let us say distance is 5 atomic units, sorry 5 A0, right, or maybe let me make it a little bit simpler by saying that the distance of the point is 5 angstroms, right. So, you evaluate it here or you evaluate at the point somewhere there whose distance also is 5 angstroms, right. Then you will find that the value of the wave function there as well as here is going to be the same, because as far as these 2 points are concerned the distance is the same, only the angles theta and phi are different, correct. So, therefore, I can go further and say that think of any point on the surface of a sphere having radius equal to 5 angstroms, the function is guaranteed to have the same value, right, and therefore, we say that this is a function that is spherically symmetric. It does not depend upon direction in space, it simply depends upon the distance of the electron from the nucleus, it is independent of the direction. So, that is the reason why we say this particular function is spherically symmetric. Okay. And further you take this part, I want to understand this part, how will I understand this part? Well, the answer is that I will make a plot of this part. To be very precise, think of making a plot of R10. R10 is actually a function of small r. I should be making a plot of it against R, and this is the functional form. So, if you look at the functional form, what does it contain? There is this constant, the constant is not dependent upon distance. So, what is dependent on the distance is this portion. This portion will change as you go to change the distance of the electron from the nucleus. And what happens to that function? Well, it is actually e to the power of minus r by a0. Any exponential function, you know, of the form e to the power of minus r by a0, you know that it is going to decrease exponentially as you go away from the nucleus, and therefore, if you made a plot of this, it will have its largest value at the nucleus, right. When r is equal to 0, this function will have the largest value, and as you go away from the nucleus, the function will go on decreasing steadily. This is how the function is. And strictly speaking, when is it that the function becomes 0? E to the power of minus r by a0, when is it that the function becomes 0? We can put r equal to 500 angstroms, still you will not have 0, but you will have e to the power of minus roughly 500, right. This object is, let me say it is 500, then you will have e to the power of minus 500, which strictly speaking is not 0, but for all practical purposes, of course, e to the power of minus 500 is 0. But strictly speaking, what will happen is that if you made a plot, it will go on decreasing, it will never become 0 unless you are at an infinite distance, correct. So, this is the dependence upon distance. I have told you that the function is spherically symmetric. So, what I want to do now is to combine these two information. I know how it depends upon distance, I know how it depends upon the angles. So, I want to combine these two informations and make a plot which will give you both the informations. How will I do that? Well, the usual procedure is to make use of what are referred to as density plots. So, if I have a function, you see the function actually will have different values in different regions. Okay, suppose you have space, the function is defined everywhere in space. At each point it will have a certain value. So, what I am going to do is I am going to represent the function by shading, simply by shading using my chalk. But wherever the value of the function is large, I will put a large density of shading, while wherever the value of the function is small, I will have a very lesser density for shading. And if the value of the function is 0, then naturally I will not have any density there. And you may run into a problem, well, if suppose the function is negative, what do you do? There again I will just worry about the magnitude of the function, right, and put shading, but then I have to tell you that in this region the function is it's negative. So, I will put a negative sign in that region. So, that is the usual procedure that I will adopt. So, if I did that with this particular function, what is going to happen? Here is my nucleus. Where is it that this function has the largest value? It has the largest value at the nucleus. So, therefore, the density of shading is going to be maximum at the nucleus, and as you go away from the nucleus, the density of shading will decrease, and eventually when you go further and further away, the density of shading will simply go on decreasing, and this is how you would represent this particular function. This is psi 100. Oh, instead of writing psi 100, I will also write psi 1s, because this is what we refer to as the 1s atomic orbit. So, this is the way in which I can represent this atomic orbit. The density of shading will be maximum at the origin, and as you go away, the function is going to decrease, correct. Now, this is the wave function, but I can, and of course, I should also tell you that this particular function is positive everywhere, right. The function, you look at it, it is everywhere positive. So, therefore, you would also indicate that by putting positive signs, and you will see that this is the way 1s atomic orbital is represented in textbooks. But then you suppose, I mean, you may say that, well, after all, it is not the wave function, but the square of the wave function that is interesting. You can say that definitely. Why? Because the square gives you probability density, right. So, if you like, you can even make a plot of R10 square, because this is the wave function. You can take the square of that, or you can take psi 100 square and construct a plot just like this, and I am not going to do that. Why? The reason is simple, the appearance is going to be just the same. It will have its largest value at the origin, and as you go away from the origin, the function will simply decrease, right. So, now I want to ask a question. What is the probability that the distance of the electron from the nucleus lies between R and R plus dr? Or to be very much clearer, I want you to think of a distance of the electron being 5 angstroms and 5.01 angstroms. So, I want to say, okay, what is the probability that the distance of the electron is between 5 and 5.01 angstroms? This is something that I want to calculate. I think I will stop here and continue in the next lecture with this question. Thank you for listening.